How did we get here? Why do we exist? What is the universe made out of, and how does it all work together to give us the beautiful things we observe? These are questions that humans have been trying to answer for as long as humans have been around. My name is Colin, and I'm an experimental particle physics research assistant at the University of Minnesota, working on 2 experiments hosted at Fermilab. When a particle physicist looks out at the world and experiences its beauty, from the snow to music to the cosmos, they want to understand how the basic building blocks of matter work together to give us all these amazing things. The cool thing is that one of these particles, known as a neutrino, we think holds the key to explaining why there's matter in the universe. That is, it can explain why we exist at all. It's our job as particle physicists to measure the properties of neutrinos to see if they could possibly play this role. But first, what's a neutrino? Neutrinos come from nuclear reactions, so they are produced in abundance in the sun, nuclear power plants, and radioactive decays. One of the unusual things about neutrinos is that they're so tiny that they can pass straight through atoms. However, every once in a while, a neutrino will happen to collide with an atom, and we can see this interaction if it occurs inside a neutrino detector. The interaction will produce a spray of particles that the detector can see, and working back from those, we can determine the properties of the neutrino just before the interaction. My research uses one of the neutrino detectors hosted at Fermilab, called the Nova Near Detector, to study the relationship between what we see after a neutrino interaction and then the properties of the neutrino before the interaction. This is what's called a cross-section. For example, one of the things we don't have a good handle on is how the properties of the nucleus of an atom affects these interactions. My research focuses specifically on using neutrinos to make a measurement of these nuclear properties so that we have a better understanding of how they affect the interaction. Because we're looking for patterns in extremely complicated data sets, my research uses lots of AI and machine learning. By hosting these experiments at Fermilab, the US is training thousands of workers who are well equipped to deploy AI to solve any number of problems. Beyond this, my research is important for every neutrino experiment because each one relies on understanding how to work backwards from observed particles to the unobserved neutrino. My contribution, along with many others, will enable current state-of-the-art neutrino experiments like the US-hosted Dune experiment to make exquisite measurements of neutrino properties, helping us to understand if they are the ingredient that can explain why there's something in the universe rather than nothing. This would affirm the United States' position as a scientific leader of the world, and the part of me that's competitive and from Minnesota couldn't be more excited about that opportunity.